Having discussed moments of forces, we're now prepared to discuss equilibrium of bodies. We'll begin by discussing the equilibrium equations. The force equilibrium equations are straightforward, but we need to discuss the significance of taking moments about one point or another. In section 5.2, we'll discuss different kinds of restraints and what they imply for reaction loads, and then we'll look at imposing equilibrium on bodies in two dimensions. In section 5.3, we'll examine additional topics starting with mechanical elements. We talked about pulleys and linear springs when we introduced particle equilibrium in chapter 3, and we'll revisit those elements again. But now there are more mechanical elements to discuss, including torsional springs and gears. Continuing with our additional topics, we'll return to an examination of statically determinate versus indeterminate problems. We also introduced this topic in Chapter 3 with particle equilibrium, but we'll come back to it with bodies. To close, we'll examine some special members, including two-force and three-force members. I've alluded to two-force members previously in our discussion of particle equilibrium, but we will now be able to prove that a body acts as a two-force member under certain special conditions. The three-force member is something we'll encounter less often, but it is a manifestation of the concurrent force system we discussed in Chapter 4. Finally, we'll examine equilibrium of bodies in three dimensions. This will also require further discussion of reaction supports, including bearings. This figure shows a general three-dimensional body subjected to a variety of forces and moments. The double-headed arrow here will indicate a moment, and you can think of the origin of this as a force couple. The conically shaped support icons are intended to be ball and socket joints, a restraint which prevents translation in all three directions. If we were to draw an enveloping surface around the body, we would have three reaction force components at each of these supports. In this figure, there would be 9 unknown reaction components between the three supports. Translational equilibrium requires us to impose force equilibrium, as shown by the first of the vector equations. Rotational equilibrium requires us to impose moment equilibrium, and the second vector equation is sum of the moments about point P is equal to 0. You'll notice, though, that no point P is actually shown in the figure. Where is P? Is there anything special about the selection of this point? It turns out that as long as we are imposing force equilibrium, we can impose moment equilibrium about any point we like and be assured that moment equilibrium is satisfied everywhere. To see this, consider the following two-dimensional problem where a body subjected to an arbitrary combination of forces and moments satisfies force equilibrium as well as moment equilibrium about point P. The question then becomes, what is moment equilibrium about a second arbitrary point Q? It will be easier to answer this question if we establish first some relative position vectors between points P and Q and the forces of interest. You'll see on this body I've drawn what's supposed to be an arbitrarily shaped body, and I've put 3 force loads and 2 moment or force couple loads on the body. And if we take moments about P or Q, we'll need a relative position vector from either of those points to someplace in the line of action of the force, and I'm going to go to the points A, B, and C that are shown here. I could establish a relative position vector from Q to A or from P to A, and we'll just make a note that we could write the relative position vector from Q to A in terms of the relative position vector from P to A by writing, for instance, the relative position vector from Q to A is equal to the relative position vector from Q to P plus the relative position vector from P to A. And we could do this for the other forces. I won't draw too many more of these because the figure is going to get awfully busy again. But for instance, I could say the relative position vector from Q to C is equal to the relative position vector from Q to P plus the relative position vector from P to C. So now I want to write an equation, sum of the moments about point Q. We want to figure out what that's equal to, given the fact that we're beginning with the premise that we have force equilibrium and we've already required, or we've already imposed moment equilibrium about point P. So on the basis of the three force vectors and the two moments shown here, some of the moments about Q could be written RQA cross FA plus RQB cross FB plus RQC cross FC. And then the moments have the same influence everywhere in the body, so I'll just write this as the moment load at D plus the moment load at E. That's the sum of the moments about point Q. Now if I write each one of those relative position vectors from Q to the point of interest, first in terms of the relative position vector that goes from Q to P and then from P to A, what I'll end up with is the following. Each one of those relative position vectors will contain a relative position vector from Q to P, so I'll end up with RQ to P cross each of these forces and then plus these terms. So it seems like I've complicated things because I had 5 terms and now I have 8. But notice that this term in parentheses is the sum of the forces acting on the object. And this bottom set of terms, these 5 terms, are sum of the moments about P. But our premise is that we've already established force equilibrium and moment equilibrium about point P, so both of those terms that are underscored with the large bracket, the large curly bracket, are 0, and therefore the sum of the moments about Q is also 0. So this is a really important result. It tells us that when imposing moment equilibrium, we can choose any point we like. For a three-dimensional body, this will give us 3 scalar moment equations to complement our 3 scalar force equations. If we go back to this figure and we consider the equilibrium of this body, we again might note that if we cut through these ball and socket joints, we would have 3 reaction components at each joint, giving us 9 unknown reactions. This specific problem would then be classified as statically indeterminate because there are more unknown reactions, 9, than there are scalar equilibrium equations, 6. And that is okay. Beginners often feel compelled to get numbers for every problem, even if the problem is posed in such a way that numbers aren't possible. In the present case, we need to provide more information than just the equations of static equilibrium to solve for these unknown reactions. A common novice response is to say, well, I can take moments about any point I like, so if I just take moments about a second point and set that equal to 0, that would give me 3 additional scalar equations. I'll have 9 equations and 9 unknowns, and I should be able to solve for all of these reaction forces. But that won't be the case. What that previous derivation just told us is that if we satisfy moment equilibrium about one point, we satisfy it about every point. You will never generate more information about a single rigid body by taking moments about additional points. There are only 6 independent statements of equilibrium that can be generated for any 3-dimensional body. If the problem is 2-dimensional, there are only 3 motions possible: translations in 2 orthogonal directions and rotation about an axis perpendicular to the plane. In this case, the equilibrium equations reduce to 2 scalar force components and 1 moment equation. Often the problem is in the xy plane, and moments are then in the z direction. Because the moment direction is unambiguous in a planar problem, we often drop the subscript, z in this case, indicating the moment direction, and just write sum of the moments about point p equals 0. It's understood that all the moment contributions are either coming out of the plane or going into the plane. The process we described in Chapter 3 for approaching and solving particle equilibrium problems will also hold for rigid body equilibrium. As a reminder, this slide from Chapter 3 has been reproduced here. Before writing any equilibrium equations, it is important to visually isolate the body of interest, drawing an enveloping surface around it and including three classes of forces, and now moments, acting on the body. External loads from the environment, often weight, internal loads exposed when we cut through connected members, and 3 reaction loads. You may notice that I have been careful to use the word loads instead of forces. Although many loads will be forces, we also now have to consider force couples, a rotational load, which we will represent as moments, an equivalent force system to a couple. Also reproduced mostly intact from Chapter 3 is this slide. Now we begin by deciding on a body to analyze. In many of our problems in Chapter 5, we will be examining a single rigid body, so there isn't much decision-making involved. As we transition to Chapter 6, though, we'll be examining assemblies of rigid bodies, and then it becomes more important to decide what to isolate. We then draw an enveloping surface around the body, sketch it, and represent all the external, internal, and reaction loads acting on it. We need to take some time to again discuss the kinds of supports we're likely to encounter and what that means in terms of reactions. Remember once again that we include a reaction component for every degree of freedom that's prevented or impeded. In this set of icons in the upper left, we have a larger variety of ways to indicate that a support is free to move in a direction parallel to a surface, whether that surface is a floor, a guide, or a rod, but is unable to move normal to that surface. In all of these, we have a single force reaction normal to the surface. If the surface is parallel to the x direction, then that normal force is in the y direction, as shown here. The 4 icons shown in the lower left all represent conditions where there is a single reaction force directed at an angle theta. The icon in the lowermost left, involving a cable with self-weight and hence sagging, is not one we will run across in our applications. The cable with negligible weight is one we've seen many times in our particle equilibrium problems, and this really doesn't require any additional explanation. What does merit additional explanation are the 2 short links shown on the right of the bottom 4 icons. It isn't explicitly stated here, but we're assuming their weight can also be neglected. If we have pin-supported links with negligible weight, those links are 2 force members, and the line of action of the force transmitted by the link goes through the pin supports. Note that the shape of the link is completely irrelevant. The fact that the bottom one is arched is of no consequence. It will again transmit a load that passes through its pin supports. We will prove this towards the end of the chapter when we examine 2 force members explicitly. There is great value in identifying a body as a 2 force member because such a body is automatically in equilibrium. If we do find ourselves with a problem where many different components are competing for our attention, it can be very useful to begin by identifying the 2 force members. This allows us to put these aside and focus on the remaining components. Focusing first on the top row, we have 2 different kinds of supports where translations are prevented, the pin or impeded, sliding on a rough surface. And we have a force component in each direction. The middle row represents the most rigid possible support. This is called a built-in or clamped or fixed support. These words are all used interchangeably. This refers to a support that prevents all motion, rotation as well as translation. It may be helpful to think of a column in a post hole footing. Concrete poured into a hole in which a post is either submerged or rigidly attached at the surface. Modest forces applied to such a column will need to be able to move it or tip it over. The moment reaction shown here may represent the resultant of a distribution of force couples around the footing. The bottom row represents a support very similar to the built-in support, and in fact the column is built into the collar. But if the collar is mounted on a frictionless rod, it has no way of passing along the force component parallel to the rod, and we're left with a single force reaction in addition to the moment reaction. Note that if the rod were not smooth, there would be resistance to motion along the rod, and we would be back to the full set of loads shown in the middle row with the built-in support. We now look at an example involving an I-beam. The I-beam is obviously the largest member present, and our attention might very well be focused here. But what can we say about the short segments helping to support it? On the left side, we have a short segment built into a wall and then pin supported at A. The fact that one side is not pin supported but built in means we are unable to identify this short segment as a two-force member. When we separate the I-beam at the support at A, we need to represent the reactions as two force components, an AX and an AY component, consistent with the pin being unable to move through its bearing. On the right side, at D, we have another short link that is pin supported at both C and D. This does satisfy the conditions for a two-force member, so the reaction force at C has a line of action that goes through C and D and is thus purely vertical. Drawing the isolating surface along the cut lines shown here, we have the free body diagram shown below. Note that there is an additional half a foot of beam length on either side of A and B, so the total length of the beam is 11 feet, and the total weight of the beam is then 26 pounds per foot times 11 feet equals 286 pounds. The weight of the beam is actually distributed uniformly from one side to the other, but we will see in Chapter 7, advancing the methods introduced in Chapter 4, that we can replace this distributed weight with the total weight acting at its effective center. In this case, the center of gravity is right in the middle of the beam, and the 286-pound weight is shown acting there. We have three unknowns in our free body diagram: the reactions AX, AY, and CY. Since we can write three equilibrium equations, we should be able to solve for these unknowns. Force equilibrium in X is particularly simple as it just shows that AX is 0. Force equilibrium in Y tells us that the sum of the two vertical reaction components must match the total external loads, 2,286 pounds. Finally, we need to pick a spot to impose moment equilibrium. In this case, we've elected to take moments about A. Using the scalar approach, we have a clockwise or negative contribution from both the weight of the beam and the 2,000-pound external load, and a counterclockwise or positive contribution from the reaction CY. Solving for CY gives us 1,543 pounds, and then we can substitute this back into the vertical force equilibrium to find that AY is 743 pounds. Before leaving this example, let's take a minute to discuss options for choosing the point about which to take moments. We should look for a point that simplifies the algebra involved in enforcing equilibrium. Point A is a good choice because the lines of action of both reaction components at A go through A and therefore have no moment arm or contribution to moment equilibrium. This ensures that the only unknown in the moment equilibrium equation is CY. We could have also elected to take moments about C. In this case, the lines of action of AX and CY both pass through C, so the only unknown force component appearing in the moment equation is AY. Employing this instead of our first moment equation about A, We have counterclockwise or positive contributions from the external loads and a clockwise or negative contribution from AY. The result is minus AY times 10 feet plus 286 pounds times 5 feet plus 2,000 pounds times 3 feet equals 0. We can rearrange this as AY is equal to 6,000 plus 1430 foot-pounds divided by 10 feet, which again gives us 743 pounds. We could then substitute this back into the vertical force equilibrium equation to give us Cy equals 1543 pounds. Note that taking moments about a different point changed the details of the procedures, but ultimately produced identical results. Is there any other point where we might take moments? We can choose any point we like, but other than A or C, the moment equation will contain more unknowns and therefore make the solution more difficult. It will turn out, when we discuss rigid body dynamics, that it is often useful to take moments about the center of gravity, G. For completeness, let's do that here. G is the location where the 286-pound weight force acts. AX will not contribute anything, again because its line of action goes through G, but both AY and CY will contribute, so our moment equation will contain two unknowns. The moment equation about G becomes minus AY times 5 feet minus 2,000 pounds times 2 feet plus Cy times 5 feet equals 0. Dividing through by the 5 feet, we could write this equation as minus AY plus CY is equal to 800 pounds. Since our vertical force equilibrium equation is AY plus CY equals 2286 pounds, we could add these two equations together. The AY's will go away and we get 2CY is equal to 3,086 pounds, or CY equals 1543 pounds. Again, there's no difference in the results, but instead of getting one of the reactions directly, we had to solve two simultaneous equations to get the reaction components. All this is a way of saying that in taking moments, you should look for a point that maximizes the simplicity of the resulting equation, making it easier to solve for what you don't know. Sometimes we can use different sets of equations to impose static equilibrium. The most physical of these three sets is the first one, the one on the left, as it corresponds to imposing translational and rotational equilibrium. An alternative to this is to write two moment equations and one force equation, as long as the 2 points for taking moments have different x-coordinates. This isn't so much introducing something new as it is rearranging the set of equilibrium equations in different linear combinations. To illustrate, let's go back to our previous example for just a second. I'm going to clean this up just a little bit. Our vertical force and moment about A equilibrium equations are rewritten here and labeled as 1 and 2. Suppose now I replace one of these equations by a linear combination of 1 and 2. I'll elect to replace 1 with minus 5 feet times 1 plus equation 2. Writing that out explicitly gives me these. Adding those two equations together gives me minus 5 feet times AY plus 5 feet times CY equals 2 feet times 2,000 pounds. But if you look closely, this new equation is exactly what we had when we took moments about G. That is, when we replace two force component and one moment equation with one force component and two moment equations, it simply represents a different linear combination of the equilibrium equations. We could similarly eliminate the force component equations entirely and impose three moment equations as long as the 3 points about which we take moments don't all lie on the same line. In the vast majority of cases, I'll stick with the first approach, that is the one shown here on the left, as I think it is most closely connected to the physical behavior. But the point is, we have options. Note, though, that we will never generate more than 3 independent statements of equilibrium in a two-dimensional problem, nor will we ever generate more than 6 independent statements in a three-dimensional problem. As a second example, we consider a simple L-shaped structure subjected to one force and one moment, that is, a force couple. There are 4 different methods of support in A through D, and we'd like to determine the support reactions in each case. Moving from A through D, we have respectively, in A, 1 pin support and 1 roller support, in B, 3 roller supports, in C, 1 built-in support, and in D, 1 roller support and 1, what is this? In case D, the icon at lower right is intended to convey that the support permits vertical translation, note the vertically oriented rollers, but not horizontal translation or rotation. The appropriate reaction components in that case consist of a horizontal force reaction Cx and a moment reaction Mc. In all 4 cases, there will be 3 reaction components, and force and moment equilibrium should give us enough information to solve for all the unknowns. Let's now take these one at a time. Most of the time I'll be careful to draw an enveloping surface around the body to show where we cut through supports, but in this case we have just the body and I'm cutting through the reaction, so I'm going to annotate the figure as it is instead of drawing a separate figure and drawing the forces and reactions separately. We have a roller support at B, so we're going to have a single vertical force component here, and we have a pin support at C, so we'll have support Cx and Cy on this side. If we now write our force and moment equations in the x direction, we simply have Cx plus 10 pounds equals 0, and that just tells us that Cx is minus 10 pounds. In the y direction, we have B plus Cy equals 0. There are no vertical external loads acting on the structure. And now we have to pick a point about which to take moments, and I'm going to choose to take moments about C. In that case, we'll have just the reaction component B that appears in the moment equation. So if we take some of the moments about C equals 0, we have first the contribution from the clockwise or negative 20 inch-pound force couple, because that has the same influence everywhere in the body. So we have minus 20 inch-pounds. And then we have a contribution from the 10-pound external load, also clockwise and through a distance of 3 inches. So minus 10 pounds times 3 inches. We also have a clockwise contribution from B through a moment arm of 6 inches. So minus B times 6 inches equals 0. And if we rearrange that, we get that B is equal to 50 inch-pounds, actually minus 50 inch-pounds over 6 inches. So that's minus 8.33 pounds. And CY then is equal to minus B, which is plus 8.33 pounds. So that tells us that CY actually has the direction that's shown. It's going up. BY is actually going in the other direction. It's going down. And again, that's not inconsistent with the roller support because that's just a schematic that tells us that there is a force provided normal to that surface. It can pull the bracket down as well as push it up. And CX is actually equal to minus 10 pounds, so it actually goes in the other direction. Okay, for part B, we have roller supports at A and B, and so I'm going to draw a single reaction here at A and a single reaction at B. We have a roller support at C as well, and now the incline, or the roller is sitting on an incline of 30 degrees. We're able to move laterally parallel to that surface. So now our line of action for C does something like this. We have a 90-degree angle here. That makes this angle 30 degrees, and our C is inclined at that angle. So now what do our equations look like? Sum of the forces in X equals 0. We have A minus C sine 30 degrees, and sine 30 degrees is a half, so this is minus 1/2 C plus 10 pounds is equal to 0. In the vertical direction, we have B plus C cosine 30 degrees equals 0. Cosine 30 is root 3 over 2, so this is B plus root 3 over 2C is equal to 0. And now the question becomes, where should we take moments? I'm going to choose to take moments about point A because the lines of action of A and B intersect at A. Neither has a moment arm. So if we choose to take moments about A, only the unknown C will show up in the equation. And I'm going to make a note here that because C is inclined at this angle, it will be easier to break C into its components. So the CX component will be like this, and the CY component will be like this. And we'll use those two pieces separately when we take moments. So sum of the moments about A equals 0. We're going to have a counterclockwise or positive contribution from CY here, and that's through a distance of 6 inches. So this is root 3 over 2C. That's C cosine 30. That's the vertical component, and it has a moment arm of 6 inches. The horizontal component is C sine 30. That's 1/2 C, and that is exerting a clockwise or negative contribution about A through a distance of 3 inches. So I have minus 1/2 C times 3 inches. And then again, I've got I don't have any contribution from the 10-pound force because its line of action also goes through A, but I do have this contribution from the minus 20 inch-pound force couple. So that single equation is going to give me is going to enable me to find C directly, and I can rearrange this as C is equal to 20 inch-pounds over 3 root 3 minus 3/2 inches. And if I calculate that out, C ends up being equal to 5.41 pounds. I can then take my force equations and plug in C and solve for A and B directly. So if I do that for the vertical force equilibrium equation, I end up with B is minus root 3 over 2 times C, that's minus 4.69 pounds, and A is just C over 2 minus 10 pounds, that ends up being minus 7.29 pounds. So both A and B actually are in the opposite direction to what I've sketched on my free body diagram, and C does have the direction that I've sketched. For part C, this problem is actually pretty straightforward because we've got a built-in support at C, and so we have a full complement of reactions. We've got a CY, we've got a CX, and we've got a moment about C. And the equations turn out to be very simple here. So sum of the forces in X equals 0. We have just 10 pounds minus CX equals 0. So CX is obviously going to be 10 pounds. In the vertical direction, we have a reaction force CY but no external load, so CY is equal to 0 pounds. And then taking moments about C, I have the moment about C. I've drawn it as counterclockwise or positive, so that's the moment reaction at C. And then I've got two clockwise contributions from the external loads at A. I've got minus 20 inch-pounds from the force couple, minus 10 pounds times 3 inches equals 0. And so very quickly here I have CX equals 10 pounds, CY equals 0 pounds, and the moment about C is 50 inch-pounds. For part D, I have this roller support at B, and I have at C I've got a reaction force CX and a reaction moment MC, but no reaction force CY. The icon is indicating that I can translate without resistance vertically. This also turns out to be a relatively simple problem in terms of the algebra. Some of the forces in X equals 0, again, gives us just 10 pounds minus CX equals 0. Some of the forces in Y equals 0 gives us B, but there's no other external load in the vertical direction, so B is equal to 0. And then if I wrote some of the moments about C equals 0, I have again my reaction MC. I've got my clockwise 20 inch-pound force couple. And then I've got my minus 10 pounds times 3 inches. And for completeness, I could, even though B is 0, if I were representing that contribution, that would be minus B times 6 inches equals 0. So even though this is a different kind of supported problem, we get a result here that's very similar to what we got in part C. We have CX is equal to 10 pounds. We don't have a CY, but now B is equal to 0 pounds, and MC, the moment reaction at C, is still 50 inch-pounds.